Hello everyone, my name is Kumar Aditya and in this video I will discuss about the fundamental of phase shift control PWM. So here I have drawn this H-bridge inverter and I am controlling it using phase shift PWM technique. So you may have come across this kind of output voltage shape in applications such as dual active bridge, load resonant converter or wireless charging. So this kind of wave shape is generated using phase shift PWM. Let's see how it works. So here on my top plot, I am plotting the gating signal for this MOSFET M1 and M3. That is the top MOSFET of leg A and leg B. And in the second plot, I am plotting the gating signal for M2 and M4. That is the both bottom MOSFET of the leg A and leg B. So you will notice there is a overlap of the gating signal for M1 and M3. There is this period during which both are overlapping. That means both M1 and M3 are turned on at the same time. And if you notice this path here, if you turn on M1 and M3 at the same time, you have this load directly short circuited through this loop here, closed loop here. So output will be 0. Similarly, when you turn on M2 and M4 at the same time as it is being done by this gate signal here, so your output voltage again becomes 0 for this overlap period, and hence your output voltage will be cancelled during this overlap period, and that's why this type of output wave shape is generated by using phase shift PWM technique. And because of the cancellation of voltage, it is also known as voltage cancellation control, and due to its symmetrical nature, that is, you can see the same cancellation happen in the positive cycle as well as negative cycle, so it has symmetrical shape. And because of symmetrical cancellation, it is also known as symmetrical cancellation control or symmetrical clamp mode control. So this is the fundamental, this is how it works, and I have put together this simulation to help you generate phase shift PWM for controlling your H-bridge in such a manner. So what I am doing here is basically I am taking two voltage source. So one is here modeling my duty cycle and another voltage source is modeling my carrier signal. So let me plot it here. So currently my duty cycle is set to 0.1 volt. So I have a duty cycle of 0.1, and second plot is my carrier signal. So I'm using a ramp of switching frequency 10 kilohertz. And from the comparison of this ramp and duty cycle, I am using this circuit to generate two PWM pulses which are phase shifted with respect to each other. You see, there is phase shift between the red and the blue trace here, and the amount of phase shift is directly proportional to your duty cycle here. So if I increase the duty cycle, this phase shift will increase. So by varying the duty cycle from 0 to 0.5, you can vary the output voltage from 0 to its full capacity. So let me just show you. If I increase the duty cycle from 0.1 to 0.4, you will notice that this phase shift will increase. You see, the phase shift has increased, and so is the output voltage. And because of this output voltage is directly dependent upon the phase shift between the PWM signal, it is known as the phase shift control. Rest of the circuit here is just to implement the dead time between the complementary pulses for M1 and M2. So I'm using this particular circuit to generate dead time, and I have given the formula here to calculate the dead time. So using this, you can adjust your R and C value to get your desired value of dead time. And you know that this whole logic will be usually implemented in a microcontroller which generate voltage of 3.3 or 5 volt level. But to turn on the MOSFET, you need 10 to 15 volt output. So I'm not talking about the logic level MOSFET, obviously. So generally you will need 10 to 15 volt output. So you will need some kind of gate driver to boost this signal. And here I'm using controlled voltage source to act as my gate driver. just for this example here. So let me just show you the dead time between M1 and M2. This is M1 and this is M2. So you see the both signals are complementary, and I have a dead time interval here. So I have adjusted the value of R and C to give me a dead time of 0.7 microsecond. So let me just put a cursor here. It should be close to 0.7 micro. You won't get exactly 0.7, but yeah, 697 nanosecond. So it's around 0.7 microsecond of dead time. So I hope this circuit is useful for you, and if you have any question, please leave that in the comment section. Bye bye.